Welcome, dear students. Myself, Dr. S.M. Thorat, Associate Professor, Sri Shivaji College of Arts, Commerce and Science, Akula, is here with a very interesting presentation on Introduction to Electrode Potential. This concept is a part of an important unit, that is electrochemistry, and it's a beginning or an introductory knowledge to study of electrochemistry. So let's begin with the topic. When a metal is placed in the solution of its own salt or in water, it has a tendency to ionize and pass into the solution. Thus, when zinc rod is placed in the solution of Zn plus ions, say zinc sulfate solution, then zinc ionizes and passes into the solution as zinc, giving Zn ions, Zn plus ions, plus 2 electrons. So in this process, the electrons are removed from the metal atoms, and therefore the process is called as de-electronation or oxidation. Nernst called this property of metal as solution pressure. There is another tendency of metal ions in which the electrons are gained by metal ions to convert into atomic state. In this process, metal ions in the solution possessing positive charge are deposited on the metal electrode and accept the electrons to be converted into the atomic state. So in this process, there is gain of electrons, and therefore it is called as electronation or reduction. Example, copper dipositive plus 2 electron giving atomic copper. Nernst called this property as osmotic pressure. Now, what do you mean by half cell and single electrode potential? First, we will discuss the oxidation potential. When zinc rod is placed in a solution of Zn plus ions, that is zinc sulfate solution, then zinc ionizes and passes into the solution, and the electrons remain on the zinc electrode. Here you can see the electrons are remained on the zinc electrode, and the zinc passes into the solution in the form of positive ions. Therefore, an electric double layer is formed at the vicinity of the zinc electrode, which is shown in this figure. So here you can see the zinc electrode in contact with Zn plus solution, that is zinc sulfate solution, and here is the formation of electric double layer, which is formed at the vicinity of the surface of zinc electrode and its solution. So because of this electric double layer formed, a potential difference is set up. And this potential difference is due to the oxidation potential, zinc giving Zn positive ions plus 2 electrons. As the potential is produced by only zinc electrode, it is called a single electrode potential. If the concentration of Zn plus ions is maintained at 1.0 molar and temperature is maintained as 25 degrees centigrade, then the electrode potential of zinc in contact with Zn plus ions is called as standard electrode potential. The single electrode potential is nothing but the difference of potential between a metal and the solution of its salt. Now, the determination of absolute electrode potential by using the single electrode is not possible, and therefore the standard hydrogen electrode, that is SHE, is used as a reference electrode. When hydrogen gas at 1 atmospheric pressure is in equilibrium with hydrogen ion of unit activity, the potential produced is said to be the standard hydrogen electrode potential, and the value is taken as 0. So therefore, the EMF of the cell is equal to the single electrode potential of that half cell. That means to determine the single electrode potential of only zinc electrode is not possible. Hence, you have to combine it with the standard hydrogen electrode. The entire cell can be represented as, see to the left hand side, this is the zinc electrode Zn in contact with Zn plus ions, which are maintained at 1 molar concentration, and this is the hydrogen electrode, platinum electrode in contact with the H2 gas, which is at 1 atmospheric pressure, and the hydrogen ion concentration, which is at 0.1 molar concentration. The cell reduction of zinc electrode combined with hydrogen electrode can be represented as zinc giving Zn plus ion plus 2 electron. This reaction is taking place at the anode, and twice H plus 2 electron. The hydrogen ions receive those 2 electrons and get converted into H2. This reaction is taking place at cathode. And the overall reaction is the sum of these two half cells, that is zinc plus twice H plus, giving Zn dipositive plus H2. Here we have written this reaction, zinc plus twice H plus giving Zn plus iron plus H2. And the EMF of the combined cell is given as EMF of anode plus EMF of cathode. Now EMF of anode means the EMF of the zinc electrode, and the EMF of cathode means the hydrogen electrode whose value is taken at 0.00 volt. So the total EMF of the cell is said to be the EMF of zinc electrode. This electrode potential is due to the oxidation of Zn metal to zinc plus iron, and therefore this value is termed as standard oxidation potential for zinc in contact with Zn plus electrode. This can be represented as E0 zinc Zn plus ions, that is the value comes out to be plus 0.763 volt. And if this value is to be expressed in terms of standard reduction potential, then the sign should be reversed, and this can be represented as E0 zinc in equilibrium with Zn plus ions, that is equal to minus 0.763 volt. Here we have reversing the sign since we are representing it in terms of standard reduction potential. Although standard electrode potential is fixed, the concentration of an ion in a half cell affects its single electrode potential, and this is given by the Nernst equation. E is equal to E0 minus 2.303 RT divided by NF into log of concentration of ion. If you substitute the value of R, the gas constant, T, the temperature, and F, the Faraday of electricity, the value comes to be 0.0591 divided by N into log of concentration of ion. In this equation, E is the single electrode potential, E0 is the standard oxidation potential, and this is for the half cell in which the oxidation occurs. So this equation we have written for standard oxidation potential. Nernst equation gives a relationship between the electrode potential and the concentration of electrolyte solution, and we represent by another form of Nernst equation. E is equal to E0 minus 2.303 RT divided by NF log of concentration of metal. This square bracket denotes concentration of metal ions divided by concentration of ions, where this E0 is the standard electrode potential for 1 molar solution of metal ions. F is the Faraday of electricity, and N is the number of electrons gained during the electrode reaction. So this is the general form of Nernst equation that shows the EMF of the cell. Now let us discuss the reduction potential. When copper rod is placed in a solution of copper dipositive ions, that is copper sulfate solution, then electric double layer as shown in the figure will be formed, and because of this electric double layer a potential difference is set up. This potential difference is due to the reduction process, as we can show by the reaction copper dipositive plus 2 electron giving copper. As the potential is produced by only copper electrode, it is called as single electrode potential of copper dipositive ion in contact with copper half cell. Now, if the concentration of copper dipositive solution is maintained at 1.0 molar and temperature maintained at 25 degrees centigrade, then the electrode potential of copper dipositive ion in equilibrium with copper is called as standard electrode potential. And this single electrode potential is nothing but the difference of potential between the metal and the solution of its salt. Now the determination of absolute electrode potential by using the single electrode again is not possible. So therefore, as we have seen in case of oxidation potential, here also the standard hydrogen electrode is used as a reference electrode for measurement of EMF of reduction potential. The EMF of standard hydrogen electrode is taken as 0. The entire cell can be represented as, now this is the standard hydrogen electrode, that is platinum electrode in contact with hydrogen gas at 1 atmospheric pressure and which is in equilibrium with hydrogen ions which are maintained at 1.0 molar concentration. So this left hand side represents the constitution of standard hydrogen electrode. The right hand side represents the copper electrode, that is copper in contact with copper dipositive ions which are maintained at 1.0 molar concentration. So it is to be noted that oxidation potential of copper is less than standard hydrogen electrode, that is less than 0 or negative, whereas the oxidation potential of zinc in equilibrium with Zn plus ion is more than the standard hydrogen electrode, that is more than 0 or positive. Now let us write the reaction which are taking place at anode and cathode. At anode, H2 gives twice H plus 2 electron. These 2 electrons are absorbed by copper dipositive ion to get converted into copper at cathode. The overall reaction is the sum of these two half cell, that is H2 plus Cu dipositive giving twice H plus copper. Now this is the reaction, and the EMF of the cell can be taken as equal to the EMF of copper dipositive ion in equilibrium with copper. The single electrode potential is due to the reduction of copper dipositive ion to metallic copper. If the concentration of copper sulfate solution is maintained at 1.0 molar and temperature 25 degrees centigrade, then the value of electrode potential observed is called as standard reduction potential, and it is denoted by E0, copper dipositive ion in contact with copper. The value comes out to be plus 0.337 volt. If you have to express the value in terms of oxidation potential, then the sign has to be reversed. And so this is the E0, the standard oxidation potential of copper dipositive ion in contact with copper, that is minus 0.337 volt. The reduction of copper dipositive ion to copper, it is denoted by the reaction copper dipositive receiving the 2 electrons to give atomic copper. According to the Nernst, reduction potential can be expressed by the equation E is equal to E0 minus 2.303 RT divided by NF into log of concentration of ion. That is equal to E0 minus 0.0591 divided by N log of concentration of ion. And if it is expressed in terms of oxidation potential, then E reduction is equal to minus E oxidation. Then the sign of this right hand side has to be changed. That will be minus E0 plus 0.0591 divided by N into log of concentration of ions. The complete cell may be represented as zinc in contact with zinc sulfate solution. Here you can see a double line that represents the salt bridge in contact with copper sulfate solution in contact with the copper electrode. So here we represent that electrochemical cell which we have discussed, and the formation and the measurement of electrode potential. Here you can see at the anode the zinc electrode in contact with zinc sulfate solution. This is a salt bridge, okay, that transfers the two solution from one beaker to another beaker, that is transport of ions and electrons take place through this salt bridge. To the right hand side we have the copper rod, that is the copper electrode which is dipped in copper sulfate solution. Okay, now this represents, you can see the arrow pointing the flow of electron which constitute the electric current and which is measured by the voltmeter. So this is the representation of electrochemical cell, and I hope you understood the concept of electrode potential, how to represent the oxidation potential and reduction potential. So thanks for watching the video, and do like, share and subscribe to get new videos. Thank you.